Can you see my screen?
Yes.
Okay. So today, my presentation is about reducing quality loss and food safety risk in perishable food distribution. My name is Amin. I recently graduated from the PhD degree at IMSC Department of University of Texas at Arlington. And my main focus of research is food supply chain, food sustainability, and food logistics and transportation. So in this topic, let's talk about some sort of economic impact of food waste. So in general, in the US, 40% of all food produced are thrown away, which is basically means 1.6 billion pounds of food, which accounts for 750 billion annually. And food waste and food quality loss also have environmental impact, a huge environmental impact. 21% of landfills are food waste. Huge amount of landfills are filled with the largest component actually of the landfill of municipal solid waste is food waste in the United States, which accounts for 18% of the methane emission in the US. It's a huge amount. So we also, losing the quality of food is also has another aspect, which is basically food insecurity. And even in the US, we have about like 1 in 7 Americans are food insecure. And if we can prevent some sort of quality loss and distribute the surplus foods among the people in need, we may even fight with the hunger and distribute this surplus food among the people in need. So also losing the quality of food will associate it with some sort of food safety risk, and it will have some sort of cost in the US. In general, in a study, it shows that about 120,000 hospitalization and 3,000 fatality each year is related to foodborne illnesses. And the cost of this sort of illnesses in the society is about $50 billion each year. It's a huge amount. So any way that we can prevent food safety risk or mitigate the risk, we can lower these numbers and it will have a huge impact. So let's talk about how foods are wasted and the effect of food quality loss and actually how food loses its quality during the time. So based on there are a specific spoilage organism that inside the food, which are basically number of this organism are growing during the time, and the growth rate of this organism is related to the is actually impacted by the temperature, storage temperature. So higher temperature means that we are having, like in this graph on T1, it shows that if we stored a specific food in a higher temperature, the slope of increasing the number of SSOs will be higher, and it will reach the maximum acceptable level that beyond this point food is not secure and safe to be consumed. It will reach this point faster comparing to the lower temperature like T2 and T3. And basically shelf life of the product will be lower, and it will reach this maximum acceptable point faster. So if the temperature, actually we know that temperature is has the highest impact on the food quality loss, and it's one of the main factor that we need to take into consideration. So let's see what will happen inside the container of a refrigerated truck through the delivery process. Imagine a truck wants to load the food in the depot and wants to deliver it to multiple customers. We have ordered from, I don't know, maybe 10, 12, even some cases more than 20 customers in a single truck or trailer. And it wants to start delivering from customer 1 through customer 20. So in the right-hand side, you can see the temperature will start with a slight increase and decrease. So any time that is when a refrigerated vehicle stop at the delivery point, it will open the container door, and the hot ambient air will come inside the container, and it will cause the increase inside the increase in the temperature inside the container. And then when the doors is closed and start continuing its way to the next customer, the cooling system will compensate this heat inside the container, and it will go down to the level of desired temperature. So basically, fluctuations of this temperature will be wider and wider when we receive, when we unload part of the cargo into the customers. And because the mass of the cold items inside the container will be lower, and the temperature will fluctuate faster and wider. So this is what is actually happening inside the container. So let's see how this will affect, let's see at first how we can predict the temperature. So let's, at the beginning, we have the distribution plan, and we want to execute the best alternative for our food distribution. So at first, we want to know, before starting the distribution process, we want to know how temperature will fluctuate through the process. So in my research, I've divided the temperature prediction into 2 phases: unloading and transportation. And I used energy balance equation to basically calculate the amount of energy that is coming through the ambient environment inside the container during the unloading, and the amount of energy that the cooling equipment compensate through the transportation. So at the time of unloading, we can use the first formula to calculate the temperature at each time step due to temperature increase at each time step of unloading. And on the second formula, we can use Tij, which basically shows the decline in the temperature based on the amount of capacity of cooling equipment at each time step. So Tij, which shows the decline in the temperature, but decline in the temperature will continue through the point that we reach these desired temperature. So basically, through the transportation, the temperature will be maximum of the decline temperature and the desired temperature that set for the thermostat of this cooling equipment. So now that we have the temperature prediction through the distribution, we can use Arrhenius Equation and Gharehyakheh model to basically consider the effect of temperature on the growth of SSOs inside food. And on the right-hand side, it shows the, for example, some solid increase in the SSOs, and but we may have fluctuations, and basically this slope of this figure can be higher and lower through the time. So Arrhenius equation will consider the impact of temperature fluctuations, and Gharehyakheh model will calculate the actually estimate the number of SSOs through the time based on the estimated values in the Arrhenius equation. So now I want to talk about some sort of concept on the quality loss. There are two types of quality loss that we can see. One of them is actual quality loss. The other one is the visible quality loss. Basically, on the literature, in the previous literature, they were not literature of supply chain and transportation. They were the quality loss was just a linear decline through the time, and they did not consider the effect of temperature fluctuation. Basically, it will be left-hand side picture. It's a linear approach. And the dashed line shows that the quality will decline with a solid linear line. But the visible quality, it says that, for example, if you put a food on a shelf through certain amount of time, which they call it quality reduction point, people are eager to pay the full price for that one because there is no visible or tangible changes on the shape or other of the food on the shelf, and it's like 100% high quality food, which is basically, it's not true on the effective quality, but on the visible quality, it's like 100% high quality food. But after a certain point, there will be some sort of visual or tangible changes on the shape or other of the food, and people are not gonna pay the the full price for this one. So the retailer should put some sort of discount or promotions to be able to sell this type of products. On the right hand side, the only difference between the right hand and left hand side pictures are the constrained effect of temperature, which is basically the main innovation of this research. So if you want to say, okay, we now know how visible quality loss actually is happening for a food before even starting the transportation process, distribution process, we can say phi can be the function of can be a function which basically says how with what probability or percentage we are able to sell this product at a full price, which is basically is minimum between 1 and 1 minus shelf life divided 1 minus quality reduction point. So if we have this selling probability, we can say, okay, we can somehow calculate the quality cost. So keep in mind that in most of the distribution objectives, the only thing that matters is cost. So we are trying to somehow transfer the amount of quality that product is losing through the distribution process into a cost. So we know that how in what percentage a product can be sold, and so 1 minus this probability multiplied to the potential revenue that we are going to lose, which is basically price of this product, plus the disposal cost, like the energy and the money that we need to pay to dispose this product, is the cost of the system for the quality loss. So in other words, till quality reduction point, if we can sell this product till quality reduction point, we are not going to pay any sort of cost, and sell probability is 1, and 1 minus 1 is 0, and there is no quality cost. But after that point, we are gradually start paying some sort of price for the quality loss. So I just want to show an example here why food distribution matters or effect on the quality loss of food with an example. So on the left and right hand side, we have some sort of similar example that some perishable food product need to be distributed from depot to customer A and B. The only difference between these two scenarios is customer B has a demand twice as the demand of the customer A. So the distance between depot and the customers are exactly the same, no major differences, only difference is the demand. So in the scenario 1 on the left hand side, if we deliver food to customer B, so the amount of time that a product needs to be unloaded is twice of scenario B on the right-hand side. Basically, food will be imposed to a high temperature for a longer time, and you can see that the temperature from time hour 10 to hour 15, the food will be exposed to higher temperature, and the shelf life will have a higher decline during this time. And but both customer A and B on right and the left and right examples respectively will receive a product with 278 hours of shelf life. But on the second customer, because we have exposed it for the longer time on the left-hand side, the shelf life will be 236 hours compared to 259 on the right-hand side, which will be lower. And basically, without any sort of difference into two examples from the point of distance and travel time and this sort of things, we are just losing some sort of quality on scenario A on the left-hand side. So in order to deal with this problem and construct this distribution model, we use vehicle routing problem time window model, and we integrated with the quality dependent module. So a vehicle routing problem with time window VRPTW will generate some sort of routes, and routes will be used to predict the temperature. Predicted temperature will be used in the shelf life prediction model, and the shelf life prediction model will be transformed into some form of quality cost. On the other hand, the generated route will has its own transportation cost, like the cost of fuel and driver and maintenance and everything. And at the end, both of these two costs will be integrated as a distribution cost, as the final distribution cost. So previously, on the literature, we only had this vehicle routing problem time window, which does not consider the calculated quality cost which we added. So let's see, after solving this problem, we somehow have two major findings. This example is similar to the example that I described. Let's say that we have two customers to visit, and we can start visiting with customer 2 on the left hand side and then go to customer 1, or we can visit customer 1 on figure B and go to customer 2. So the only difference is the sequence of this delivery, but both customers at the first stop will receive the 99% of quality. So basically there's no big difference, but because of the time of unloading at the first visited customer, the second customer on scenario A, sorry, we received 87% of quality, comparing to second customer on scenario B, which are receiving a 97%, which is a huge difference, 10% difference. So it's one of the way that considering the quality cost will improve the result of vehicle routing problem. And it can be said that the transportation costs are similar, 618, but the quality cost on the vehicle routing problem is 310, comparing to quality 170 in the quality dependent vehicle routing problem time window, which is basically much higher. We also investigated other options. So basically vehicle routing problem and distribution problem is so complicated, and there can be some other spots that this problem can be impacted by the quality dependency. The other one that we found is this one. So let's say now we have 3 customers, and we have this option to just use one vehicle to deliver to all these 3 customers, or divide this delivery between two vehicles. So on scenario A, vehicle will start from depot, will visit customer 2, and then 3, and then 1. And on the right-hand side, on scenario B, we have vehicle 1, which is basically going to visit customer 3 and 1, then come back to depot. And vehicle 2 will visit only customer 2. From the transportation cost point of view, for sure, scenario A is better. 634 transportation cost, considering 765. Using one vehicle is cheaper, or it will need less travel time and physical travel time comparing to using two vehicles. But on the quality point of view, it's a big difference. On the scenario A, customer A will receive products with just 86% of quality, which is basically much lower to comparing to 96% that customer 1 will receive on the scenario B. And the same thing is happening for customer 3, which is basically receiving 88% comparing to 99%. So we are losing lots of quality on the vehicle routing problem scenario. Scenario A, 300 is the cost of vehicle routing problem comparing to 80, which is basically the total cost of the quality dependent vehicle routing problem with time window is lower than the total cost of the vehicle routing problem. So we started to investigate this problem in different size of problems. So as we increase the problem size, the alternative solution that we have and the flexibility and the complication of this problem will grow, and the gap between the quality dependent vehicle routing problem and the improvement of this problem comparing to the vehicle routing problem will be much higher. And for a small size, maybe the solutions are the same, but on the medium size and the large size, it will be a higher difference. So we added this with the some sort of sensitivity analysis. If we have consider lower shelf life and the higher SSO growth rate associated with the higher sensitivity to temperature, we have 3 products: poultry, frozen meat, fresh cut salad, and Gouda cheese. And we sorted with low and high and medium level of sensitivity to temperature respectively. And considering the market price for each of these 3, we can see the quality cost and temperature transportation cost, which each of these products will be somehow for the low and medium, the quality cost will be the same. For the high sensitive one, the quality cost will be much higher, which these differences will be reflected on the transportation cost as well. So as a main conclusion of this research, we can say that temperature inside the container of refrigerated vehicles significantly increases when it stops and unload, when the door of container is open to unload the products to a customer. High temperature elevates the growth rate of SSOs inside the food, which means that the rate that we are losing the food quality, which be much higher, will be much higher. And the prediction of temperature and shelf life provide an accurate estimation of food quality. We use this one to calculate the quality cost. And we calculated the quality cost based on the loss in revenue and the discarding cost, and then we added to the objective of this food distribution model. And we discovered that the sequence of delivery and frequency of stops can have a huge impact on the quality cost. And also the characteristic sensitivity of food to the quality and the cost of food, it has has a huge impact on the routing decisions. So basically, I can just quickly show you the resulting publication, which is basically we used some sort of multi-objective approach. We added the vehicle emission consideration, environmental impact, and everything. This research is recently published in Sustainability Journal of MDPI publisher and in May 2020. If you are interested, you can see more results and the whole model and everything in this paper. And it will wrap up my presentation, and I will be happy to answer any question that we